So first step as usual is to find the UI and armature resistance value. But let me illustrate what is happening here. We know the torque versus speed diagram for a shunt excited motor. It is a straight line. Yes. Now it is connected to a centrifuge, which is some kind of mechanical device, right? Which is used to separate liquids and stuff. And as it speeds up, it needs more and more torque. So the torque demand of the centrifuge is like this. And we need to find this intersection point, which will be the operating point, because at this RPM, specific RPM, the motor is supplying the torque which is required by the centrifuge. If we were here, the motor is supplying more, so that the RPM will increase. If we are here, the motor is supplying less than the demand, so RPM will decrease, and it will eventually reach this point. And the nominal operating point of the motor can be here, we do not know. What we do know is it's slightly different.
Sorry, I can you again tell me about the steady state operation in this graph?
So what we do know is the torque demand from the centrifuge. It is modeled by this k naught n square and n square. So parabolic, like exponential term. So we have this parabolic graph.
Okay.
Shunt excited motor has a straight line torque versus RPM. I mean, this is not a straight line, but basically I was trying to draw a straight line.
Okay.
Is it? Something like that, right?
Okay.
So this is at this is the operating point,
Hmm.
because this is the only RPM where the motor is supplying enough to meet the demand of the centrifuge. Look at other RPM which is to the left of this point.
Hmm.
Look at this RPM. Here the centrifuge needs only this much torque, but motor gives much more, which means there is excess torque available. So the centrifuge will accelerate. It will use this excess torque to accelerate I alpha. It will be spent on I alpha, and so it will keep accelerating until it reaches this point, and at this point the motor is supplying exactly what is needed for the centrifuge, so the I alpha term has to become 0, so it stops accelerating and it stabilizes at this point. And we need to find this point. We don't know at what RPM this is happening. We need to find this.
Okay. Okay.
Yes.
Okay. Hmm.
So step 1 is as usual. UI is K1 phi n. I will keep K1 phi as a single term. For that we need UI now. UI is from Pn. So Pn equals UI times In. So I'm using the nominal case to get this K1 phi value, which I can use for all the other points in the motor. So
Hmm.
UI equals 10 into 10 power 3 watts divided by current is 55 amps. This gives me 181.8 volts. Armature resistance is U nominal minus UI divided by I nominal. So 200 volts, right? Yes, 200 volts minus 181.8. 181.8 volt divided by 55 amps. This gives me 0.33 ohms. So far, it's the same process which we are doing for any motor question. We are finding the induced voltage, we are getting the RA value. From induced voltage, I can get this K1 phi value.
Okay.
K1 phi equals UI divided by N, but this N I will have in terms of seconds like we did previously.
Hmm.
So, what is the nominal RPM? It is 5000 divided 5000 by 60. This will give me how much? 2.1816 volts second. So this is 1 by second.
2.18418. It's okay.
Okay, now we have K15. Let us use the torque equation. Torque is equal to U K15 divided by 2 pi Ra minus K15 whole square by 2 pi Ra times N. This is the equation we have.
Oh, hmm.
So this is directly from the slides. Torque in terms of RPM.
Hmm.
So
Torque.
I'm going to use that same equation, and this is the what the motor is giving. What my target right now is to find the steady state RPM.
Hmm. Hmm.
So like I mentioned previously, steady state point where A equal to alpha equal to 0. So RPM is constant and there is no net force or net torque anymore. And that is happening here when the both the torque supply and demand are equal. It's kind of like economics. You have this point where supply equals demand.
Okay.
So similar story here. So I can equate the supply U K15 by 2 pi Ra minus K15 whole square N by 2 pi Ra to K naught N square. And look what I have now. I have a quadratic equation. So if I
Hmm.
rearrange and I substitute the values, I get 2.27 into 10 power minus 3 n square plus 2.1816 square divided by 2 pi into 0.33 n minus 200 into 2.1816 divided by 2 pi times 0.33 equal to 0. So 2.27 into 10 power minus 3 n square plus 2.29 n minus 210.43 equal to 0. So if you solve this, you should have two solutions. One
Hmm.
of which is 84.768 1 by second. I cannot recall what the other solution was. I will calculate it right now. Just one moment.
It's 84 and minus 1093.5.
Okay. So 84
And
into is
minus
minus 103.
1093,
103, right?
1093.5.
93.5.
Yeah. Yeah.
Wow, okay.
This is obviously wrong.
Yes. So the RPM can definitely not be negative. It's not something we are expecting. So this is just some numerical answer we are getting. So that's not correct. So meaningless. It's like having negative time kind of. So this is our
Okay.
actual RPM. I mean the actual rotational speed. Here it's in terms of seconds. So n in RPM would be 5086.12.
Hmm.
Usually it is a good, it's good if your design is having RPM higher than nominal, because then the slip, like, okay, there is no slip here, but just imagine it's somewhat like slip. So you can run it faster, it's fine, but running it slower means you're pulling more current which it's not rated for.
Hmm.
So the operating point can be to the right of the nominal point is in a good design, should be.
So now we'll calculate torque.
uh Yes, now you can calculate torque. Now we have the RPM. It's just a matter of substituting in the equation. So this equation, if you substitute, you will get torque. So the hard stuff or the confusing part is actually equating these two and finding the RPM, steady state RPM. And once you have this, you can substitute back in the equation. So
So the still the answer. Okay. Okay.
now we should definitely match. U K15 K15 square. Remember to have the RPM, like not RPM, rotational velocity or rotations per second, right? Use that. So U is the supply voltage, not induced voltage. So 200 times K15. K15 was 0.186. No, what? 2.1816 volt second. So volt 2.1816 volt second divided by 2 pi into 0.33 ohm minus 2.1816 square volt square second square by 2 pi into 0.33 ohm multiplied with 84.768 1 by second. So if you solve this, you should have the answer. 200 into 2.18 minus 2.1816 squared times 84.768. So I'm getting 32.876 divided by 2 pi into 0.33 Newton meter. This gives 2 pi 0.33 15.85 Newton meter. Question asked is power. So power equals torque times omega, which is 15.85 Newton meter into 84.768 into 2 pi radians per second. Answer into 84.768 into 2 into pi. So that gives me 8.445 kilowatt.
Hmm.
So that's how you solve this question. It's a different type of question, I'm aware, but that's why I included this. It's kind of harder, definitely harder than what you can expect on the exam, but if you know how to solve this question, any question on the exam should be easier.
Okay. So, I have one